So this was a problem that we didn't quite get to because the problems from last time were just a lot of fun. So what we were doing, we're talking about triple integration. Ideas are pretty simple, straightforward, split things up into pieces and add them up. The way we do it intuitively makes sense. It's sort of like we're going to add an extra layer. And so we get to do not 2 integrations, but 3 integrations. So we integrate one at a time. Now the tricky thing, if we can call it a tricky thing, is saying, well, what are the bounds? How do we find these bounds? And even more to the point, the more challenging point, is how do we change the bounds? And so that's what we were talking about last time. So we're going to do a little bit more practice because these are types of problems which are good to know because they really test geometrical intuition. And in a lot of sense, that's what Calculus 3 ends up testing you on, is do you have that good geometrical intuition? And if you do, you're probably going to be okay. And if you don't, well, time to practice so you can get that going. All right, so here's our first example for today. Let S be a solid bounded by a couple of things. Z equals 0, y equals 0, y equals x, and z equals 2 minus a half x squared. And we're asked to write this integral over our solid f of x, y, z dv as an iterated integral. In other words, we're going to have a triple integral and work on our bounds. So let's start by trying to understand what our solid looks like. Now there's a couple of things we can see. Z equals 0. Now, one of the things we need to understand is where are we? What's our setting? And the answer is, our setting is, we're in 3-dimensional space. Now, the way we know that is, for one thing, while we're doing a triple integral, we see our f of x, y, z, and we look at these bounds and we see all the variables showing up, x and y and z. So it's like, okay, so we're in 3-dimensional space. So when we say z equals 0, we say, okay, what does that mean? This really means that this is a plane. So this is the plane z equals 0. Well, which plane? So we should probably sketch that, or at least know which plane we're referring to. So if I have my coordinate system, here's my x, y, and z, and I want to figure out what the plane is, well, where is z equals 0 in this diagram? Yeah, it's the xy plane. It's this plane here. So that's sort of the floor. So we have z equals 0 is this bottom part here. Okay, now let's go to our next one. Y equals 0. Well, where is that? It's the xz plane. Okay, well, we also have the xz plane in our picture, so we can sort of sketch that in as well. So I have here the xz plane. All right, so there is another one of my surfaces. So far, pretty simple. I'm optimistic that we can actually get a good picture. Okay, y equals x. Well, what is that? So if we were in 2 dimensions, in other words, suppose there were no z, and we said y equals x. What would we be? We'd be a line. And it's a very famous line. It's a line we see a lot. And so I could come into the xy plane, which is the z equals 0, and I could draw the line y equals x. So let's say this is the line y equals x, at least a portion of it. Now, that's, of course, if I were in the xy plane. But now I go to 3 dimensions. So y equals x, what does that become? It's a plane. And how do I know how to draw it? Well, as someone has said, it's a line, and you just copy up and down. Because notice, there's no z variable showing up. And if there's no z variable, it means you get the same thing on every level. So what it ends up being is it ends up being this plane. And so here we go. This is our plane, y, equals x. All right, well, that's a little bit faded there. Maybe we'll make it a little bit darker color because we want to refer to it later on. Okay, so far so good. We've got 3 planes coming together. Now, are we done? Well, no, one more to go. But so far, we're feeling pretty good. Our last one, z equals 2 minus a half x squared. Well, let's think about that. First off, notice it only involves x and z. So one way to think about it is say, let's start in the xz plane. And in the xz plane, what do we look like? We look like a parabola. It's, in particular, it is a parabola that's been turned upside down, scaled a little bit, but shifted up. So if I were to go over here and say, all right, I want to sketch this curve, z equals 2 minus a half x squared, well, I could come up, find where z equals 2, and then I'd be going down. All right, so there's part of our parabola. Now, I stopped when I hit the plane because we're not going to be going below the plane. That's one of our bounds. Now what happens? Well, the answer is because there's no y, you just copy that straight across. And you're going to keep getting this same shape. All right. So those are our surfaces. Now, of course, it comes down on the other side. But what will we see? Now, it's a little bit crowded in here. So let's clean our picture up. And we're going to trim away the parts that we really don't need. And once we do that, here's what we'll get. We're going to see the following shape. So here, 2, and kind of a curve going there. All right, so it looks a little bit like a tetrahedron in that it actually is very much like a tetrahedron, except instead of having all the faces be flat, one of them is curved. And that's what's happening. So where are my faces? Well, they're as follows. On the back here, this is my plane y equals 0. On the bottom, I see z equals 0. Back over here, this is the plane y equals x. And then the curved face, that's my z equals 2 minus a half x squared. All right, so those are the 4 surfaces that make up this shape. Good. Now we know what our shape looks like, and we're ready to begin the problem. What are we after? Well, we want to write the integral as an iterated integral. So that means integrate in some particular order. So now we get to make our choice. Which order should we integrate in? So what are the options? Well, we have dx, dy, dz. We have dx, dz, dy. We can do dy, dx, dz. We could do dy, dz, dx. We could do dz, dx, dy. Or an oldie but a goodie, dz, dy, dx. You pick, and we'll go through. dy, dx, dz. It has been chosen. dy, dx, dz. Now, what's the process? We have our shape and we know our surfaces, so we're going to set up our bounds. So what we're going to end up with is we're going to end up with an integral, triple integral, because there's 3 variables here. Our function is always going to be the function. That doesn't change. And then we have the order dy, dx, dz. Now, you've chosen a very interesting order, but that's great. We like interesting orders. So, to begin with, what do? Well, I set the bounds going from the outside in. So, I see that going from the outside in, my last bound I'll set is the y bound. Well, if the last bound I'm going to set is the y bound, a good thing to do is start by looking down the y-axis. So I'm going to look down the y-axis. So down the y-axis, what will we see? Well, what we're going to see is we're going to see something in the xz plane. Because when I'm looking down the y-axis, I don't see y anymore. In fact, y is that point, what you might call the origin point. All right. So now you have to sort of visualize. What do you see? What do you see? Yeah, you see the parabola. So this z equals 2 minus a half x squared. This front face is going, so this whole face here, that's the front. When you're looking down the y-axis, because there's no y, that surface becomes just a curve. And what curve does it become? Well, it becomes the curve where I have z equals 2 minus a half x squared. And of course, similarly, z equals 0 becomes z equals 0. And then I'm going to have this last part, which is the intersection of y equals x with y equals 0. Well, if y equals x and y equals 0, then x has to be 0. Which means that when I look down the y-axis, I'll see that shape. Good. Now we can start to answer a couple of questions. So let's work on our questions. Where does z go from? 0 to 2. Fantastic. And we're looking for numbers. So that was easy. Now we go to our next layer. So I have z. Next thing to do is to figure out what happens with x. So I have z, and I'm going to say, where does x go between? Well, what is x on the left-hand side? That surface, or sorry, excuse me, that curve. It's 0. Now, what is x on the right-hand side? Well, it's not 2 minus half x squared, because I need to go x equals 0 to x equals something. So what's our next step? Solve for x. So we do a little bit of arithmetic, some of our favorite things here. A half x squared is 2 minus z, or x squared is 4 minus twice z. And so x is plus or minus, but I'm positive x, so the square root of 4 minus 2z. All right, so there's my x value. So I can now fill that in. I go from x equals 0, that curve, to x equals the square root of 4 minus 2z. All right, that's that layer. So we did numbers. Next one we did curves. Going into our last layer, go back to our three-dimensional picture. In our three-dimensional picture, what's happening? Well, now what's happening is I'm moving in the y direction. So I'm going to go from one surface to another surface. So notice here, my line right now is in the y direction. So I'm just moving between surfaces and y. What's the back surface in terms of y? It's y equals 0. Because when I asked in terms of y, because you notice it's dy, so it's going to go from y equals to y equals. So the back surface is y equals 0. What's the front surface? Y equals x. And so the bounds are going to go from 0 to x. All right. Now, what happens next? We're done. We set it up. Well, that was quick. Let's do another one. Okay. We did dy, dx, dz. Let's try a different order. We have enough time. We can do one more order. Pick an order. There's 5 left. What? dz, dy, dx? dz, dy, dx. Okay. All right. An oldie but a goodie. Now, why do I say it's an oldie but a goodie? Well, if you do dz, dy, dx, that's the way that you're used to thinking about things. Okay, so let's do dz, dy, dx. So we're going to have integral, 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 f of x, y, z, dz, dy, dx. When in doubt, if they don't give you any other suggestions, that's probably the best one to start with. All right, so which axis do I look down? I look down the z-axis because that's going to be the last thing I said. So I'm going to say, let me simplify my picture so I can see what's happening. So I'm looking down the z-axis. As I look down the z-axis, what do I see? So down the z-axis, what we're going to see is we're going to see something in the xy plane. And as people have been noting, what we're going to see is this triangle here. Now, can we say things about that triangle? We should be a little bit careful. It is a triangle. That's not the part where we have to be a little bit careful. Where's the part we have to be a little bit careful? Well, now the question is, where does the triangle hit? Oh, in fact, that is the wrong picture. That's why you have to be a lot of careful. Okay, well, I have plenty of space. That was just showing you, mwahaha. Okay, okay. Now, where are we? Well, we are on the x, so this x part translates here. We come over to here, and that translates to that part, and then we come down. That translates to that part. Good, okay, now at least I know the right picture. Now, it's not too hard to spot a couple of things. For instance, this line is the line y equals x. This bottom line is the line x equals 0. The thing we have to ask is, what's this last part right here? Because we need to know that if we're going to set up our bounds. Now, how do we answer that? Well, let's figure out what's happening. That happens when I look at this surface. Where does the surface z equals 2 minus a half x squared, where does it hit on the axis? So, how do I find that? We set z equals to 0, because that's where I'm going to have the surface hit the axis. So to find that point right there, that one I'm pointing at, that happens when 2 minus a half x squared equals 0, which is the same as saying that x squared equals 4. So what's the right value for x? 2. And I can see now I messed this up again. That should be y equals 0, but that's okay. We can fix all of this in post-production. And x equals 2. Okay, now at least everything's labeled correctly. Whew, good. Now we're ready to go. Let's talk about x. Where does x go from? 0 to 2. Okay, now I know x. Y is going to range. Well, where is it ranging from? 0 to x. Y equals 0 to y equals x. All right. This is not my best problem, I can tell, but that's okay. We'll get the answer right. Now, the last layer. We need to get z. Well, go back to the picture. We no longer look down the axis, we actually look at the whole picture. And now we're letting x vary. So I say, okay, where does x go from? Well, sorry, not x. We let z vary. Where does z go from? Z equals 0, the bottom, and then it's going to go up until it hits the curved face, which is 2 minus a half x squared. So it goes from z equals 0 to z equals 2 minus a half x squared. And that's it. Okay, well, I better not do another one because there's not any space. That's why. Of course that's why. All right, good. So what's the topic? Now, the topic for the remainder of this session, and the next one, is to talk about applications. So when we're talking about applications, what we're looking for is we're trying to say, I want to find something. And we're going to use integration to find it. Now, in general, when we talk about integration, it's saying, what's the total? And the way that we approach the problem is to say, well, I can find the contribution of little pieces pretty well. In other words, locally I can approximate great. And so we're going to take what we're looking for, break it up into small pieces, and say what happens on each piece. Then we're going to add them all back together, and that gives us our answer. Well, it gives us a pretty good approximation to our answer, and the idea is in the limit, which is where that integral comes from, it is the answer. Now we have some geometrical applications that we've talked about. So suppose I want to find area. Well, if I want to find area, I can integrate 1 dA. Now, what's the logic? Well, what am I doing? It says, if the integral says break things up into little bits of pieces. And then you say, okay, the size of each piece is the dA. Now, what's the contribution from each piece? And the answer is the dA. And so when we add the pieces up that we broke into pieces to start with, we're just going to get the area. Same idea. If I want to find the volume of a solid, I just set up the integral, and I integrate 1 dV. Now, another option, which we've talked about before, which was a motivating idea, says, what if I want to find a volume between surfaces? So, in other words, I have a bottom surface and a top surface, and I want to say, what's the volume between the two? And the answer is, you integrate the difference between the two values. Essentially what you're doing is you're integrating height. So if you think about it here, this g of xy minus f of xy is acting as our height. Now, one way to build up the intuition is to go back and think about what were we doing last year. Well, in 2 dimensions, we talk about maybe I have a curve on the top and another curve on the bottom. And I want to say, well, what's the area between them? The answer is we take top minus bottom and we integrate. Now, a side note. Sometimes we're not going to explicitly tell you what R is. Well, how do you find it? Well, to find it, that's like finding, back in Calc 1, where were these points of intersection? Well, so now we do the same thing and we say, where do the surfaces intersect? And that'll give us where our region is. Well, that's stuff we know. We want to do something we don't know yet. So our goal for the next little bit is surface area. So I have z equals f of xy. It's some surface. And I want to find the area of the surface over a particular region R. All right, so how are we going to do it? Well, again, what's the idea? We start by breaking things into pieces. So I have my little bit of R on the bottom. So here, this part downstairs is in my domain. And then on the top, upstairs, I have my surface, z equals f of xy. And what I want to do is I want to say, well, how much area is there in the surface? Now, what I've done is I've taken a very small piece. So you notice it's not changing very much, but it won't change very much when I am looking at a small piece. And the same process, of course, our answer is going to show you how you do it for any surface, but the key is think small piece. Well, what's the philosophy going back to integration? The idea is look for a flat thing. Okay, so do we have something flat which we can find to help us approximate surface area? A plane is a very nice flat thing, and we can also probably find a pretty good plane to approximate the surface. Do we know any good plane that helps us approximate a surface? The tangent plane. So here's the idea, is now we're going to say, look, I have my surface, but I also here have my tangent plane. And the tangent plane, if I'm nearby my point of tangency, so the point of tangency, I just picked a corner. So there's my corner here. You'll see it actually matches exactly. Now, as I move away from my point of tangency, my tangent plane and my surface start to deviate. But when I'm small, they don't deviate by much. So that tells me that if I want to get an area for the surface, I can get a good approximation if I can figure out the area for this tangent plane. So now we have a plan. A plan is good. So we're going to figure out how do we approximate the area of the tangent plane, get an estimate, And then we're going to put those estimates together and get our area. Okay, well, do we have a way to find areas for things that look like this part of a tangent plane?
Length times width.
Length times width. Oh, that's true in a sense. If it was perfectly square, these don't actually have to be perfectly square. And it turns out they can be slightly off square. But it's not a bad idea. Now, downstairs, let's assume that this is a nice perfect rectangle. What we can conclude is that upstairs, it's not just any shape, it's a very particular shape. In that if I look at the sides here, if I dig into our old geometry notation, they run parallel to each other. And similarly, the sides over here also run parallel to each other, which means that our little thing that we're looking at, which is flat, is a parallelogram. Do we have a way to compute areas of parallelograms? The answer is yes. Cross product. Now, we said 90% of the time that we use cross product, we're going to use it because a cross product of two vectors is perpendicular to what we start with, and we're like, perfect. We're going to use it to get our normal stuff. But then there's that 10%, which is today. What's the area? So if I have two vectors, and I take the cross product, and then I take the magnitude of the cross product, that'll give us the area. Now the good news is we're going to actually do the math once and get a simple formula out at the end. So we have to know what the vectors are. So in our case, it turns out that our tangent plane, you can write that as change in z is the partial derivative with respect to x, evaluated at your point of tangent c, times the change in x, plus partial derivative with respect to y, evaluated at your point of tangent c, times change in y. So that we can actually get a good handle on what's happening with our picture. So if you come to our picture here, what we have is that this direction downstairs, this is our change in x, and this direction downstairs is our change in y. And what's happening is if I come up here and look at the vector, well, notice I'm not moving at all in the y direction. So this vector is going to have something, comma, 0, comma, something. Now the something in the first coordinate is how much we change below, because it's the same change. You can actually just see it's always the same amount of change. So the first entry is change in x. And what's the last entry? Well, that's where we get our tangent plane in. The answer is it's the partial derivative with respect to x times the change in x. And if you do the same idea for this other direction along this side, you're not moving at all in the x direction. So that's going to be 0. You move change in y in the y direction, and then your z part will be f sub y, change in y. So those are our two vectors that correspond to the two sides. And so now we take their cross product. And when we do that, we run through the math. So we have that the area is the cross product of the two vectors. Well, some things we can do. Notice that in the first vector, both terms have a change in x. So I can pull that out. That's common. Similarly, both terms here have a change in y. I can pull that out. So I can simplify and say, look, pull that all the way out. So you get a change in x, change in y on the end, which is our bit of area. Now, that's a cross product. It's not hard to do, I know, because that's the answer. So the cross product is minus f sub x, comma, minus f sub y, comma, 1. And then we have change in x, change in y. And we take the magnitude, and so we get the square root of 1 plus f sub x squared plus f sub y squared. And the delta x, delta y becomes delta a. Okay, so that is the amount of area approximately over one little piece. Now, what happens next?
Because the piece gets smaller.
Well, we take the pieces smaller, but we also add them up. So we add them up. So we have our sum. There's two sums here because essentially you can think of there's two directions. There's an x direction and there's a y direction. So we add them all up, and each term that we're adding is an approximation for the area. And now, as things get smaller and smaller, our approximation gets better and better until it becomes exact. So the surface area you can find by integrating over your region R the square root of 1 plus f sub x quantity squared plus f sub y quantity squared. All right. Now that's what we're going to use. That's what we need. Well, let's try this. So find the surface area of the saddle z equals x squared minus y squared over the unit circle. So here, when it talks about over the unit circle, that tells us about R. So R is going to be a nice shape. So there's R, the unit circle. Okay. Now, we can start. So we have that the surface area is the integral over our region R of the square root of, because I'm copying the formula, 1 plus f sub x squared. What is f sub x? 2x. 2x squared. Plus f sub y. What is f sub y? Negative 2y squared dA. All right. Well, it asks us to find it, not just to set it up. We want an answer. We deserve an answer. We've come this far. We want to know it. We can clean this up a little bit. We can write this as integral over r, the square root of 1, and then I'll have 4x squared, and I'll also have 4y squared, so I can write it as 4 times x squared plus y squared, and dA. Well, how should we go about integrating such a thing? Polar. Now, what are some things that suggest polar? There's two things that are hinting at polar here. Yeah. First off, the fact that our region, it's really nice in polar coordinates. The unit circle is a very clean thing to work with in polar coordinates. But there's an even bigger hint that we should go with polar. Yeah. When you see x squared plus y squared, it's practically shouting, polar! It's supposed to be in polar! Because x squared plus y squared becomes really nice and clean. All right. So we have an idea, a plan. And our plan is to do this in polar coordinates. So let's figure out what this will become. Well, what will the function become in polar coordinates? Square root of 1 plus 4r squared. What will the dA become? R dr d theta. Okay, now let's get to our bounds. Where does theta go for the unit circle? 0 to 2 pi. And where does r go? 0 to 1. Okay, now the nice thing is this is an integral. You can actually break this up because you can say, look, I have the integral with respect to r. It doesn't involve anything with theta, and I have the integral with respect to theta. So, okay, so just doing our little casual trick here. Integral 0 to 2 pi d theta times integral 0 to 1, square root of 1 plus 4r squared, r dr. Now the first integral, we can do that pretty quick. That's 2 pi. We're not going to dwell on that. How do you do the second integral? Yeah, use substitution. What's the correct thing for you? Well, probably the best thing is to just go all in and say, look, the whole thing underneath the square root. Because oftentimes when you're looking for a substitution, you say, what's on the inside? That's a good place to look for substitutions. Then, what happens to r dr? Well, if I take the derivative of u, I'm going to get 8r dr. So r dr, I can say, is 1/8 du. That's what it'll turn out to be. So, this becomes what? Well, this becomes the integral of u to the 1/2. There's a 1/8 in front, du. And we'll change the bounds. So when r equals 0, what will u be? 1. When r equals 1, what will u be? Well, u will be 5, because remember, u is 1 plus 4r squared. It's just the inside of the square root. Okay, well, what's the integral of u to the 1/2? Yeah, it's 2/3, because you're going to, first off, it becomes u to the 3/2, and then you put 2/3 in front, and then I have an 1/8, and if you multiply 2/3 times an 1/8, you'll get a little bit of cancellation, so it becomes 1/12, and then we're going to evaluate from 1 to 5, which becomes, well, 1/12 times 5 to the 3/2 minus 1 to the 3/2, which is 1. And 5 to the 3/2 is 5 to the 3/2. There's not much you can do with that one. Okay, so our final answer is, don't forget, we also have a 2 pi. And so our final answer, putting it together, is pi over 6, because the 2 goes into the 12, 5 to the 3/2 minus 1. And there we go. Life is good. All right. Well, let's do a little bit more practice. Okay. Set up, but do not evaluate an integral to find the surface area over the region where y is between x, y is less than or equal to x, is less than or equal to 2 minus y squared for the function. And it appears I did not write a function down because we're doing a setup problem. Now it's your choice. What would you like the function to be? What function have you been like, I've always wanted to know the surface area for that function? Anything? Anything?
2.
You've always wanted to know the surface area for 2? That's not a very complicated one to find the surface area for. But I can put a 2 here to start us. How about we throw an e to the x in for fun?
Cosine y.
Cosine y. Okay. Are you satisfied? Is that sufficient? Yeah. I mean, the point here is this is just let's test the formula. Okay, so the formula says that the surface area is going to be, we'll write down the generic formula, integral region over r, square root of 1 plus f sub x squared plus f sub y squared dA. All right. So in our case, well, what will we have? The integral. Then I'm going to have the square root of 1 plus, what do I get when I take the derivative with respect to x? 2e to the x cosine y squared plus, what do I get when I take the derivative with respect to y? Negative 2e to the x sine of y squared. All right, are we done? Yeah, we got to get our bounds. So this is a good chance for us to practice setting up bounds. So let's see, what do we have? We have these curves. We have the curve y equals x. So here's that curve, y equals x. And then I have another curve, x equals 2 minus y squared. What does x equal 2 minus y squared look like? Well, it's a parabola. Which way am I facing? To the left. Yep. Because x equals y squared is a parabola that opens sideways. The minus flips it, so it goes to the left. The 2 shifts it over. So it's a parabola that opens something like that. All right. Well, I want to be between these two, which means I want this region in between here. Now, we should make a choice. Which is the better choice? Should I integrate dx dy, or should I integrate dy dx? The right choice, well, not that there's a wrong choice, but the right choice is dx dy. Now, why do I call that the right choice? And then I also simultaneously say there is no wrong choice, because that seems to be contradictory. Dx dy says we're going to slice horizontally. Now, why is horizontal slicing better than vertical slicing?
You don't have to break down.
Yeah, it comes down to how you break up. You'll notice that when I slice horizontally, I'll always have a consistent left-hand side and a right-hand side, which means I just need a single integral. Whereas if I sliced vertically, you'll see initially it's like, okay, I have the line on the top, the parabola on the bottom, but then at some point I have to switch, where it's the parabola both on top and bottom. And anytime you have to switch the bounding curve, that means you have to do another integral. And usually it's better to do fewer integrals than to do more. So that's why here it's a better choice to do a horizontal slice. Now, we're getting close. We're almost there. What's the last thing we have to figure out? Well, we've got to figure out, where do these intersect? So how can I figure out when does x and 2 minus x squared intersect with each other? Set them equal. So when do x and 2 minus x squared match? Well, that's the same as x equals 2 minus x squared, which is the same thing as x squared plus x minus 2 equals 0. And cross our fingers, does this factor? If it factors, how does it factor? X minus 1 and x plus 2. So where are my intersection points at? So they're at x equals 1 and at x equals negative 2. Okay, so the good news is we're also on the line y equals x, which means that this point is at 1 comma 1, and this point down here is at negative 2 comma negative 2. All right, we're ready to set our bounds. We are integrating dx dy. Where does y go between? Negative 2 up to 1. So the lowest y value is negative 2, the highest y value is 1. Given that I'm at a particular y value, where does x go from? So I'm looking for an x equals to an x equals. So the left-hand side is x equals. Well, I'm asking the question, what's the left-hand side? Okay, yes, x equals y. The right-hand side is, whoops, I said the right thing, but I wrote the wrong thing. That should have been x equals 2 minus y squared. Right-hand side, 2 minus y squared. My copying skills are subpar today. Double check the work. Okay, so there's the integral. All right, in the last few minutes, let's try one more, because we don't have to evaluate this one either. Set up, but do not evaluate an integral to find the surface area over the region 0 less than or equal to theta less than or equal to pi, and 0 less than or equal to r less than or equal to 3. What does that look like? It's a circle. It's actually the top half of a circle in the plane. It's a full circle. What's the radius? 3. Okay, so that's our region R, and our surface is z equals r cubed sine theta. Oh, look, it's been a while. It's good to remind ourselves there's other coordinate systems. So here, we're now describing our coordinates not by Cartesian x and y, but by cylindrical coordinates. So z and r and theta. Okay, so what do? Well, what's our formula? Our formula, if we go back to our formula, it's based off of Cartesian coordinates. So that's a problem. To use the formula, we have to be in the right coordinate system, because this is a formula which is based off of working in the Cartesian coordinates. So, what do? We convert to Cartesian. So, we have z equals r cubed sine theta. So I want to get z in terms of x and y. So I can go back and say I'm back in my Cartesian coordinate system. So how can I change r cubed sine theta so it looks like things that look like x and y? Yeah, r squared and r sine theta, because r squared is nice. What is r squared? X squared plus y squared. And what is r sine theta? Y. So x squared y plus y cubed. So now I'm in a coordinate system where I have a formula. Okay, so what do we get? Surface area is the integral over my region, the square root of 1 plus, what will f sub x be? 2xy squared plus f sub y, which is x squared plus 3y squared squared dA. Now, to finish, we have a choice. We can either convert our region into Cartesian coordinates, or we can say, now that I'm here, let's go back to polar, get back into r and theta. Which is the right one? Well, the answer is they're both right, but you have to do one. So in the interest of time, let's just switch back to polar. So square root of 1 plus 2 r sine theta, r cosine theta squared plus, because I'm running out of space, I'll write it below, r cosine theta squared plus 3 r sine theta squared squared. And then the dA is r dr d theta. Theta goes from 0 to pi. R goes from 0 to 3. And that will find it for us. All right, that is it for today. And next time, it's a heavy subject. It's a lot of mass involved.